Okay, thank you for introduction. So that's interesting, but my talk can be actually kick-started from several slides of the previous speaker, Egon, and that's kind of nice coincidence. So I'll start my talk with the question, what's common between IDE and the FireTorch? And I'll give you an answer in a minute, but as we're going today to talk about visual representation of code, let's take a quick look at how we work with code today. What we use is called textual programming, textual representation of code, which basically means using sequences of words, numbers, and punctuation marks to represent code, the same way as we represent natural languages. So we interact with code much the same way as we interact with normal language. We read it from left to right, like in Western languages, from top to bottom. And because of horizontal writing system, code tends to grow downwards, so we scroll up and down constantly. So typical code reading session looks like this. You open your code in an editor, and you start scrolling usually down, sometimes up. Then you jump between functions, you jump between files. That's typical process that we all do every day, right? But let's zoom out a little bit and see what exactly is happening here. In fact, you're sitting in front of the wall of text, and you're using this sliding window to navigate the text so you can bring it closer to you and see what is happening here, right? But it's not entirely accurate. You don't see the rest of the code, so let's dim the lights. It's super dark here, but you probably see the point. Now you can see that your IDE is basically a lightning device that shines light on this wall with text, so you can even read what's written there. If you just imagine a FireTorch here, you will see that it's not really that different from the ancient ways of interacting with paintings or with text. So you just like hermit in a dark cave using its FireTorch to highlight the walls and see the paintings or the writings. So that's exactly that's my face when I read unfamiliar code base. So you see how ancient our way of interaction with code is, and of course there is nothing wrong with being resembling ancient, but I have so many issues with that. We spend 90% of our coding time, dev time by reading code and only 10% writing it, and those 90% happen to be my least favorite parts. Whenever I need to read the big code base or pull request, resembling that man in a cave. This process requires incredibly good attention. And like previous speaker mentioned, it basically, we're limited by our brain. We can keep only 4, 5, 7 things at a time. And it's stupidly tedious process. And even more, there are studies on code comprehension using eye tracking software, and they confirm that we read code very differently from text. We don't read it line by line, like the text. We jump between blocks. We fixate gaze on cognitively challenging parts of the code, and so on. So, clearly, text is not the best way to represent things. And I'm not obviously not the first person frustrated with that, and there is a whole field of visual programming languages, or VPLs. They roughly could be divided into 3 categories: block-based, flow-based, and basically all the rest. Block-based visual programming is basically environments where you don't enter code as a text, but rather drag and drop predefined blocks into the scripting area. You might have heard about languages like Scratch, MIT App Inventor, Google Blockly, and so on. And those languages mostly focus on teaching programming basics to the children and novices, and they virtually make syntax errors impossible, which is kind of nice. There's also a lot of hybrid languages that allow you to convert textual representation to the blocks and vice versa. And there are actual studies that confirm their positive effect on this young cohort of students, but that's mostly their limit. And many people believe it's not visual programming at all, it's just replacing keyboard input with the mouse input, which kind of I agree with. So the next large group is the so-called flow-based languages. Flow-based languages are based on the idea that you can represent with the flow diagrams. You can represent like state flows or data flows or logic flows. And sometimes the reasoning behind that is that logic should be implemented by the person who knows problem domain well, like doctor or engineer. And actual translation of this logic into the code is a task for another person or program. And there are several attempts to make a general purpose flow-based visual languages like Raptor, Visual Logic, Flowgorithm, and so on. But I think the highest popularity this approach gained in the very niche fields like 3D designing, shaders designing, music synthesis, IoT, pipelines, signal processing, and so on. So that's actually like a lot of people using this right now. But again, those very, very specialized tools, those not are general purpose languages. And there are a lot of harder to classify things, like, for example, Prograph. It's the language designed in 80s, and it's a modern reincarnation that you can actually run on Mac OS X, and it's like first truly object-oriented visual programming language. To me, it was still incredibly hard to use, but it has some ideas that I liked. So there are hundreds of different visual programming languages has been developed in these 60 years, but there is no truly mainstream visual programming. We still all use textual representation for all major languages. Why it's so? And my answer to that is that we just don't know what exactly we're doing. We just brute force in different options with visualizations and with textual languages as well, hoping they will work better. But there is no commonly agreed scientific explanation of what is programming, right? Like, what happens in your mind when you read or write or even think about code? Like, through the lens of which framework you can even validate if visual performs better than text, right? And I never seen satisfying answer to these questions. And if you try to answer those questions yourself, you inevitably end up in the realms of either philosophy or neuroscience, or both. So I took the blue pill, and kind of reading books on brain and cognition became a hobby of mine, and I think it helped me starting seeing all this question in like new light. And while neuroscientists just barely scratching the surface of how our brain works, and I'm just barely scratching the surface of what they're scratching, I think I can share two important insights that will help understand this topic better. So let's do very, very quick brain 101. So the human brain consists from 90 billion neurons and around 1 trillion of connections, and it's the most complex object in the solar system. So no way it can be explained easily. And most people think about brain as this wrinkled walnut-shaped thing, but it's actually a flat tissue of the decent pizza size, 5 millimeters thick. It just had to be folded to fit the skull. And it's remarkably uniform in structure. It has the same 5 layers of neurons organized in cortical columns. And those cortical columns are believed to be the single computational unit of neocortex. And presumably it does one thing. It takes insane amount of inputs, extracts patterns from them, and learn how to predict them. So the consciousness, high-level thinking, long-term memory, self-awareness, that's just a byproduct of having this immense scale of those computational units. At least that's one of the theories. So speaking about patterns, there are fundamentally 2 types of patterns in the universe, spatial and temporal. Spatial means related to space, and temporal means related to time. Space and time, here and now. This difference stems from the very nature of our universe, so brain kind of learned to handle them accordingly. Vision, for example, deals mostly with spatial relationships. That's what allows you to read this text, for example, even if you don't see the lower half of the picture. Your brain recognizes patterns in these white lines and can predict what will happen in the lower part. It can fail, of course, but that's okay. World not perfect. And the temporal relationships, better described with music. You can't hear the song by listening all sounds at once, right? They need to be stretched in time. And what's interesting that you can actually represent temporal patterns in a spatial way and vice versa. And that's exactly what's happening with musical notations, for example. It's the temporal information represented in a spatial way. But in order to understand this, you have to train your brain to decode it back into the temporal so you can like simulate and play it in your head. And for example, to me, just lines. I can hear this music, right? So that's the first thing I wanted to know. The second thing is that all our knowledge somehow stored in neocortex as well. And there was a theory about grandmother cells popularized by this Jennifer Aniston neuron study. They presumably found the neuron that spikes only when you see Jennifer Aniston and not any other celebrity. But of course, there is no such speciality in neurons. We already know that this tissue is uniform. And there is another study from, sorry, that's video, actually, it should play video. Okay. So that's actually 3D animation put online where they mapped those pieces of knowledge labeled when the person was seeing some TV show, and you can actually like move it and click and see which part of brain responds to which concept or knowledge, and you can see that semantically close things they kind of sits together. But what really defines function of the neuron is their connections, how and whom they connected to. And those connections are collectively known as a human connectome. And connectonomy is a new field, emergent field in neuroscience, and it's quite exciting. They try to map all those connections and build like computational model and simulate it on a computer, and it's incredibly hard task. But the point is, those connections are growing and rewiring and updating all the time throughout our lifetime. And those are physical connections. They really like grows, it's like real molecules. And whenever two things in your head, like you learn some association between them and it's straightened, you have like physical connections between groups of neurons. So I'm not trying to make it look simple. It's anything but simple. And I hope if there are neuroscientists watching this talk, they will not go mad at me for oversimplifying things. But still, I think this captures the point that each one of us has the internal physical map of reality in our head. So two things, spatial versus temporal, and brain as a map of reality. Now, let's talk about code. What is coding? What is programming? When people start learning new programming language, they ask, what should I practice on? Can you give me some example to solve? What problem can I solve? There are whole sites devoted to this, right? And that's because we don't write code if we don't have a problem. And by problem, I don't mean like something bad happens. I mean something that comes from the real world, from the outside. So let's call it problem domain. So programming is not writing instructions to the computer, not anymore at least. Essence of programming is to internalize the problem domain and build mental model of the problem domain, understand it, and capture the insight in the form of the programming language. So in a way, we have a two-degree map of reality. First map is your mental map in your head, and the second map is your code. And I really like term map here because we know that map is the reduction of what it represents. Maps are imperfect by nature. And I think tools we use for mapping should really embrace this. But the real challenge with code as a map is to make this map reversible. You have to be able to read the same code and restore the same mental model in your head. And I mean really those same groups of neurons should be excited when you read the same code. And that's super hard. But to make things worse, you have to make it work for other brains as well. You have to make sure that they will build the same, as close as possible, the same mental models in their head as well. And that's much, much harder than you might think, because you can't rely on your knowledge and your mental models anymore. You have to validate your code through the mental models of other people. So it's like incredibly complicated thing. That's where social aspect of programming comes in, right? So now I start the most selfish part of this talk. Let's go deeper how we read code, but I can speak only for myself. So how do I read code? Every problem you ever solved with code is a spatio-temporal by nature. It has both spatial and temporal components. Spatial captures objects and their relationships, and temporal capture changes over time, their intricate interplay between each other or the external world. So when I read code, the first thing I'm trying to do is to capture the spatial relationships encoded in this map, in this code. For example, I'm reading HTTP library code, and I have some knowledge about HTTP protocol. I have some like mental model, imperfect, obviously. So I'm expecting to see things like client server, request, response, header, URL, and that's exactly what I'm looking first. I'm trying to understand the structure of the code, and I'm looking into, yeah, that's dark. I'm building those links from the actual lines of code to my knowledge, to my mental map. And that's where naming becomes important, because to establish those links, you have to use some shared vocabulary and some sort of shared symbolic representation. Right now it's words. I don't know, maybe in future that will be icons, some super rich emoji. That could work, but for now it's just words. But that's why naming is the most complex problem in computer science, right? So when I built this model and it makes sense, I'm going to fill in the temporal aspect. I'm going to read the text of the functions. And it's interesting, but kind of obvious, but text of the function bodies differs from the rest of the source code in a way that it encodes time. Each line will be executed after the previous one, right? That's why we have these debates about go-to keyword, because it breaks flow. Or we have defer, which cheats on this time flow, and this is cool. But it's important to understand that that encodes it encodes a temporal aspect. So that's, my friends, I think, where the answer to the question of efficiency of VPLs and textual programming language lays. Visual representation is really great for capturing spatial relationships. Text is good for temporal. So we would love to be somewhere in this sweet spot. But what happens in reality, that visual programming languages, they try to encode temporal aspect, and they try to invent new symbolic representation. And it's just incredibly hard, and networking effects kicks in, and it just doesn't work. So visual should be left probably only for capturing spatial representation information. Even more, they do not harness in the power of visualizations. Everyone who works with data visualization, data visualization knows how easy to mess up the visualization just by choosing wrong colors. So this Venn diagram here doesn't make sense, but it looks cool, right? It's visual, it's like nice, round. So that's the problem with VPLs. And that's finally where I can start talking about Go. Go is a language that gets this mapping process absolutely right. It embraces imperfect nature of maps and allows you to map things as simple as possible and makes reading those maps much easier process. And I can't help but remember here Gottfried Leibniz, German mathematician and philosopher whose mathematical notation we all use today. Among other things, he was obsessed with pursuit of perfect language, the language that satisfies 3 rules. First one, I should be able to say exactly what I mean. Second, you can interpret what I said exact meaning. And third, I can be sure you have interpreted me correctly and fully. He didn't succeed, of course, and somehow ended up inventing binary system. And number 3, I don't even think achievable realistically. But Go, to me, is the language that really tries hard to play well with those 2 rules. And if you programming language designer and you're watching this talk, please design your language for mapping, not for statistical self-expression, and be obsessed with those two rules as well. Even more, Go somehow captured very well this difference between spatial and temporal information. For spatial information, it gives you just concrete types, nothing more. For temporal, you have functions and methods, and also interface to generalize on this. And that's like compared to the class-based languages, where class means everything and nothing at the same time. It could be behavior, it could be data, it could be nothing, it could be everything, but most of the time it's just accidental complexity. Go makes this distinction very clear. So when I read Go code, I usually do not have problems with understanding like what exactly author tried to say here. So I'm not saying all Go code is good. There are a lot of bad code, of course, but it's usually a problem with the mental map it encodes, not with the encoding itself. So I started thinking about this, and like, so if I'm building this internal spatial pseudo-visual map in my head, and Go makes this decoding process easier, so maybe I can try to formalize those rules. So I will very briefly like go through some of them. For example, if I see like dependent packages, they kind of like a graph in my head, like that goes main package goes up and upper, and those go down, and they connected. The same goes with types. Types are connected to the package they belong. And that's interesting, but in my head, I'm kind of resolving this orders and priorities. So in text, you can just place one type above another, and it can hint about priority, but maybe not. So I'm trying to like capture this and understand and resolve in my visual representation. It's not visual like AR, it's like pseudo-visual. So the same goes with methods. The same goes with types. So for example, here, I don't care if it's pointer or not pointer, it's still like belong to the same package. So this kind of resolving. Interfaces are interesting because in Go, you do not create interface before you have concrete type. First, you have to have concrete types, then you see them, they have the same common behavior, and you generalize on them. So I see them kind of like cloud that kind of brings those types together. And of course, naming. There are special names like new. It's not special, it's just convention. So they kind of closer to the type. And names like start, stop, push, pop, things related, they also kind of group together, clustered. So I asked the question, can I kind of offload this task to a computer? Can I, so this building this spatial relationships map in my head takes a lot of time, and that exactly the problems that Egon described, that we have limited attention span and we can like understand well, so this trade-off between width and depth. So maybe instead of doing this all in my head, simplicity of Go can finally allow me to offload this to the computer, because less is exponentially more. So that's exactly the program I started to work in. And so how it works, it reads the code for me and builds three-dimensional model of the major concepts, trying to capture their relationships in the same way how I would do this in my head, as much as possible. So this is how it looks like. For example, container list package. You open it, it's like happens immediately, and you see that, okay, there is two types, element and list, and there are some methods that comes out from them. Currently, I'm not capturing it's like 30% or 20% of what I wanted to implement, but it's just question of time. But you can see how they relate, and you can see actual code already, like immediately. You can figure out how big this function, for example, and just to make clear, like There is no highlighting, there is no more sophisticated ways to interact with it, but it's simply because of, it's still 3D programming, it's still hard, and I'm just learning. So, for example, new here, method new, it should be linked to the type, not to the package, but again, this is still work in progress. So another example, so this is how interface works. It runs in the browser, by the way, and written obviously in Go. It's written in Vecti framework and using Gophers.js. So yeah, and the main challenge I'm having here is how to actually visualize that, how to resolve all those, links between very complicated objects, and I'm using force-directed layout algorithms and with customized force, and it's like really tricky. It's funny how our brain works poorly with physics, with different physics constants. It's like you can tune one value for the spring force, and like nodes goes bananas, goes to infinity, and that takes a lot of time. But I hope you like getting the point of what I'm trying to do. So instead of building those relationships in my head, I'm trying to create rough 3D model that will allow me much quicker figure out what concepts this code even like talks about, right? And I'm exploring different options to visualize, or different options to interact. Probably I will play with Vim plugin that you can like click on the method or function, and immediately your editor will just pop up there, or maybe editing inside the browser. And yeah, it's basically experimentation. So I don't think if I have the screencast here where it captures dependencies, but that's another nice moment, that usually when you import dependency, just single line. It's super easy to neglect. But with this visualization, you can actually see what this line brings to your code, like this huge elephant, right? So that's another aspect I really like. So yeah, that's basically it. That's a not call graph. It's not what you see in the P-Pro, for example, output. It's very different because it doesn't gives you the whole way. It doesn't like unroll this. You still have to read functions called. You should still have to like understand the call graph in your head, but presumably it should be much easier. What else? I'm not trying to invent new way to visualizing things. I'm just trying to capture what already my brain does and kind of formalize it. So it kind of visualization, but it makes sense, hopefully. And also interesting that there is a conference devoted to these algorithms for graph layouts, and they all try to make algorithms they work nice with like any graph possible. I have opposite task. I want this layout to be nice when the code is nice. But when code is crappy, when code is complicated, I want it to look terrible. And I think it works so far. So yeah, what I'm trying to do also is to move to a dogfooding stage. So this tool is written in Go, so I can actually use this tool to kind of operate to change itself, right? I think that's boosting productivity with development. It's still a side project, and obviously I would love to have like much better 3D. Probably move outside of the browser, but like if you have to share something with the world, you have to do this in the browser. Vecti will be supporting WebAssembly soon, so I will be checking on that as well. And definitely I'm waiting for the time where we all use augmented reality. Because, in a HoloLens, they presented this concept, which is like really looks similar to what I would like to. It's unfortunate that programming keeps us in a sitting position. I would like to be able to walk to the part I'm work on and be able to bring some piece of code closer to me and bring them apart and so on. But the major change and what boosts my curiosity is that I expect if this like visual representation of code that become possible because of the Go simplicity, if I'm going to use this like on daily basis, that will probably change the way how we write code, because a lot of problems with complex code is because of this fire torch. It's hard to see how your changes affect the overall structure of program if you just see the small part of it, right? And this visibility of the whole structure should definitely change our code as well, and hopefully contribute to the battle with complexity. We shape our tools, and thereafter our tools shape us. So I'm really interested in feedback. It's like first time I even showing this to anyone, and I'm kind of excited and terrified both. And I kind of gave you a sneak peek into my head, which is creepy. So especially if you're interested in this topic, and especially in the visual programming languages, feel free to write me. I will be happy to talk about this. And yeah, thank you.